All right, so I was just talking about this in the last video, the six principles of for relative dating. Okay, so um, and you can just look at these obviously. So thinking about the horizontal layers and then this idea of superposition, the cross cutting, which I wanted to get to show some concrete examples of that, and then this lateral continuity, and then and of course inclusion, and then lateral continuity, and then the faunal succession. So faunal succession has to do with living, dead organisms, of course, that were once living, and they're looking at their fossil records. Okay, and then of course there are these. It's not this. If you look at the rock formations, you don't always have this nice layering where it's always the oldest rock, because of course the Earth undergoes deformations, right? So if that happens, and there's gaps in the rock record, for the in terms of relative dating, that we call those unconformities. Anyhow, an angular unconformity happens. So this is there's actually some good pictures of this. I think it's better than these pictures. Hold on, let me see if that's kind of what I wanted to get to. Here, let me find the other picture and I'll show you what I'm talking about. So we're just talking about angular unconformity. So this is a nice picture of this. It's just showing. So this is what we mean by the angular, right? And this is the normal thing that you would see is each layer is horizontal on top of the next, and then of course as you go down further and further, you're going further and further back in time. But the problem is you get to this layer right here, and things are at an angle, and of course that's what we mean by the angular unconformity. And all that's happened is there's been some upwelling, on one side to kind of make that angle, and you can actually see this in mountains sometimes. All right, so this is a very good example. So look at these layers. I mean, these are at very extreme angles in this mountain formation. So this is a very good example of these things that were originally laid down horizontally, and because of mountain building, this outcropping, these things are at great angles. All right, so I just wanted to show a nice picture of that. All right, so let's see. So we were just talking about these angular unconformities, and I just showed you some pictures of mountains where that's an extreme situation. All right, so now let's go back to this this idea of igneous intrusion. Okay, so here's a good example. They call these this just a geological term. They call these dikes. If you look here, you have all these different rock layers, and then dike A, dike B, and dike C, and they want you to, just by looking at these, which one is oldest and which one is youngest. Okay, so keep in mind that the idea here is that with these igneous intrusions is the dike, for the dike to pass through. It has to pass through something that's already been there, that's older. All right, so if you look right here, it looks if you look, it looks to me like C is the oldest. Well, why? Why is C the oldest? Right? It has nothing to do with the angle or anything like that. But C had been existing. Like you look at it, and then B passes through. Right? So the only way for B to pass through C is if C already existed. So C is going to be older than B. And then for the exact same token, So notice A passes through B. Do you see that? So A passes right through B. And so B must have existed before A, right? And so A would be the youngest, and then comes B, and then comes C. All right, so which one would it be? So A is so C is the oldest, then B, and then A. All right, so B, the answer is, they shouldn't have labeled it A, B, and C. Yeah, anyhow, that's the answer, is that C is the oldest, right? And then comes B, and then comes A, all right? And because, just for the reasons that I mentioned before, that, because B passes through C, C had to be there first, right? It had to be there before B could pass through it. All right, so let's move on. Embedded rocks, inclusions in sedimentary rocks are they're what? Are they are they metamorphic? Are they older than the sedimentary rocks? So remember, that's here's some granite inclusions in this layer right here. Are they younger than the sedimentary rocks? Or are they the same age as the layer? All right, and so remember, for this relative dating, when we're talking about these inclusions, the inclusions are always, it's like you remember the example that they gave is when you make concrete, you're going to have pieces of rock that are older, of course, than the concrete, and so these pieces are always these pieces of embedded rock are older than the sedimentary layer that they happen to be in. All right, so B is the correct answer. They're older than the sedimentary rock. All right, so there we go. All right, so now we turn to what's called. So remember, what we were just doing is relative dating. One rock is older than another, and you just keep comparing the rocks. But then you want to have an absolute scale to be able to measure these things. And so what we do is we use what's called, so the general term is radiometric dating, and that's, in other words, it's using radioactive materials, which of course we had back in chapter 13, using half-lives, right? So remember, there's certain isotopes that have, that are radioactive, and when they undergo radioactive decay, they produce what are called daughter atoms. All right, so let's look at these are the common ones that are used for radiometric dating, and there's a reason for this. Okay, so let's look at this. Uranium-238 has a very stable daughter atom. So you might recall this from chapter 13 as well, that it actually goes through several steps before it gets to this. So there are many daughters that lead to a stable daughter, right? So there's all the daughters after uranium-238 are radioactive as well, but they eventually lead to they go from uranium-238 to lead-206, right? And that overall process to go from uranium-238 to lead-206 takes 4.5 billion years, right? And the other thing that really needs to be mentioned, and this is really important, that you don't find the isotope lead-206 very often. That's a very rare isotope. And in fact, what we can do is when we find uranium-238, all the lead-206 came from the original amount of, all of it is a product of the original uranium-238, right? So that's an important idea, right? And the same thing goes for uranium-235. That's a different isotope of uranium. Notice it has a different half-life, but that uranium-235, which by the way is really rare, And why is it so rare? Look, there's its half-life. It's not even 1 billion years, right? So, there's a lot less of it around than the uranium-238. Anyhow, uranium-235 becomes another very rare type of lead-207, and it does that. Again, it doesn't do it in one step. It does it in multiple steps, but when it does, it takes the overall, this process 235 becoming lead-207 takes 704 million years, right? So, and then of course there's potassium-40, which we encountered before. That turns into argon-40. That takes a process of 1.3 billion years, and then carbon-14. This number is wrong. Right? It's I don't know why they did that. The half-life is 5,730 years. All right, you might remember that from chapter 13 as well. Anyhow, the carbon-14 has a half-life, and it will eventually turn into nitrogen-14. Right, so now, in other words, because of the half-life of carbon-14, you can only measure, so you probably multiply by 10. And so you can measure stuff up to about 50,000 years, roughly 50,000 years, all right? In other words, if there was carbon-14 around during the time of the dinosaurs, right? So you're talking about more than 65 million years ago. That carbon-14, that's essentially all been turned into nitrogen-14. There's been way too much time. So if you go more than 10 half-lives, so remember, each of these is a half-life. If there's more than 10 of those that have gone by, then there's essentially all the original radioactive particles have become their stable daughter product. Okay, so that's the idea. So you're not going to try to date anything older than maybe 50,000 years. But like with potassium-40, you can date stuff that's billions of years old, right? With uranium-235, you can date stuff that is, maybe up to 70 million. I'm sorry, up to so 10 times that would be 7 billion years, which of course that's older than the age of the Earth. And then of course uranium-235 you can use to date stuff that is billions of years old. All right. This one would be kind of an intermediate. All right. So radiometric dating gives the actual age of rocks. The exception to the actual age can be found. An exception to the actual age can be found in. Let's see, some metamorphic. So not here. Let's just read each one. All right. So radiometric dating can give the actual age of rocks. The exception to this actual age can be found in sedimentary rocks and some metamorphic rocks, igneous rocks, metamorphic rocks, or the answer is actually A here, because you can do the radiometric dating for an individual. Not the rock, right? Because the rock is changed. Like sedimentary rock has material that has been piled up on top of it, but you can date the individual minerals. That's fine, but you're not giving the age of the rock for a sedimentary rock. And then of course for metamorphic rock, the problem with metamorphic rock is that once it heats up, all the information that you had about from the radioactive substance is gone, and so the clock starts again. All right. So, once it melts, once it